Hello and welcome to the BrainScales hands-on tutorial. Today you will get an introduction of the hardware itself and the system and how you can execute simple experiments on that. First, I will just give again a short introduction to the hardware and its parameters and features. So you can see below here is a photograph of the ASIC, which represents a physical model of 512 ADX neurons, which are running in analog, and communication is digital, so mixed signal. And the parameters of this ASIC are chosen in a way that the dynamics of the neural models run on an accelerated scale compared to real time, about a factor of 1,000. And the parameters of these neurons and their synapses, as well as the topology of neural networks that you can create, are configurable. One of the main features of this new generation of ASICs is the embedded processor, which enables the programmable plasticity and also the experimental control, for example. And another feature is the support of compartmental neuron models, which you also will learn in this tutorial. Another feature which we'll not cover in this tutorial is the non-spiking matrix multiplication mode, with which you can basically also use the chip in a more traditional machine learning way. So what you can see here is basically one of the setups with a single chip under this plastic cover, and a lot of periphery for power supply and communication and control of the chip. So another a little bit more detailed overview of how the chip looks like, you can see in the schematic. So at the heart of the chip is the analog network core. The main features are the neurons and their synapse array, which can be configured to emulate different networks. So these are basic. So you can configure them, and they continuously run then on the hardware. So they are not a classical simulation where you solve numerically the differential equations, but the hardware really is a physical emulation of the neuron dynamics. And additionally, on the chip itself are then units that handle the event input, output, recording of voltages and so on, and also the processor itself, which enables the plasticity kernels. And this chip then is, as already said, controlled by FPGAs, which can control the experiments, which themselves are then controlled by the host computers, or in this case, the IPython notebooks that you will be using. The thing is, you don't really need to know all these details, because the software framework that we will be using today will provide a more abstract representation of how you can describe experiments in a graph-based description in population of neurons and their connections. So then I will now move on to the first slide that you all should have access to. So sorry, I'm just quickly reading the chat.
Although I just posted the path, so maybe if you want to, you could show once again where to find it. And I've also see this red box over there in the upper right-hand corner of your notebook, so you may run into trouble later with the.
So I mean, basically, if you start in such a collab thing, you can search your collaboratory, open the collab that you have, and then click on click on lab, And there you can select, I mean, it shouldn't really matter. You can either select one of these, and then, yeah, your collab session should be starting. And there you already should have a version of this. For you, it probably looks a little bit different, but
yes, it should be then in brain scales, in the subfolder brain scales, and then the brain scales 2 demos.
And then in a subdirectory, you should have this folder which contains the tutorials. And today we will be covering some of these tutorial underscores notebooks and not the rest. So yeah, so everyone should then. So yeah, best just give a sign if you are, so a reaction in the Zoom call if you are on this page. That would be great. And if you have still issues, please give a thumbs down or something like this. Okay, so I don't see any thumbs downs or issues. Then I will continue. So yeah, here again, you can see a rather nice picture of our ASIC. And yeah, first we provide a short list of publications which either describe the properties and capabilities of the chip, or which describe experiments done on the chip and guide as an example of what is capable to, what you can do with this ASIC. Then today we will cover some of these tutorials. So I will start with the single neuron experiment. There I will show in rather detail some of the properties of the analog hardware and how you can use it in Pine. And then later on, my colleagues will introduce the SuperSpike learning rule and how you can use the Pine framework to emulate it or utilize this learning rule on our hardware. Then we will skip the matrix multiplication tutorials. And after that, Jakob will present a possibility of how you can use the plasticity processor on the chip via Pine. And finally, he will introduce and explain a bit about the structured neurons. So this part, you basically, if everyone already sees this page, this should be fine. And again, if you somehow delete something on accident or something like this, you always can just make a new checkout of the demo slides if you want. So we have roughly 20 people here, so we don't have that many setups here in Heidelberg. But what we have is a shared hardware access service, a microscheduler. We call it Quiggledy, which basically takes out from the experiments that you will be executing. The part that is running on hardware will just be automatically extracted, sent here to Heidelberg, emulated on the hardware, and sent back to you in your notebooks.
I have one request in the chat.
Yes.
Zoom in a little bit on the text that you show in the notebook. It's very small.
Yes, sorry. I hope this helps. Not ideally. So is this better?
I guess so.
Yeah. So yeah, I mean, basically you don't really need to understand it, but it's the magic that everything should just work as it is, but it's not a simulation running on your IPython notebook, but really the actual hardware execution is scheduled here to Heidelberg and the results are sent back to you. So then just to check that everything works for you, you should execute these 2 cells. And if everything is running correctly, yes, this should not help. Yeah.
You're missing a point, I think, from static helper plasticity, or there's like a mix-up what you import.
Yes.
From static helpers, you inserted plasticity,
yeah,
which is wrong. And maybe we should mention that you have to change the kernel probably at the top right.
Yeah, this is also.
Well.
So we will do this demonstration. So in eBrains, there are several kernels available at different states. So yeah, everything is versioned somewhat probably, but we are today using the basically latest version of the kernel, so the experimental release kernel. And if you select the wrong kernel, I mean this we can just demonstrate. If you select the wrong kernel, you will get an error that hopefully states that you are running the wrong kernel and should select the proper kernel. So just again run those 2 cells, and if everything is correct, you just shouldn't get any output. So then again, I would ask to give a thumbs up or down if you have any issues, that I know when I can continue. Okay, I don't see any issues yet. So then we will start with the first proper tutorial. As I already mentioned before, the single neuron experiment. So goal of this experiment is just to get you familiarized with the properties of the analog hardware and get to learn a bit about Pine and how to use it in our framework. So the first cell is again just setting up the hardware environment so that everything is scheduled automatically in the background. Then in the second cell, we have some imports of typical stuff like NumPy and some widgets that we will use in the tutorial, which provide slider for ease of use. And then here the important import is the Pine Brain Scales module, which is a version of Pine specialized for our hardware. So Pine, for that of you that don't know it, is a domain-specific language which has the goal to provide a way to describe neural network experiments in a simulator, or in our case, emulator agnostic way. This doesn't completely work if, as you will see in the following tutorials and slides, but it's a rather close approximation. So, and then again, just a helper function that will print the results of the experiment. So mostly membrane traces and spikes. So first we will just look at one of these neuron circuits on our hardware. In this case, just a silent neuron, which doesn't do much, but let's see how this can be set up in Pine. So first we need to initialize Pine, and then we simply define a population. A population is just an ensemble of one or more neurons, which most of the time have same parameters. In this case, we just define one. And Pine normally provides a set of different neuron classes, like leaky integrated fire neurons or stuff like this. Yet we don't, or until now, we don't support these intrinsic neural models, but have a rather specialized neuron, which is just a one-to-one representation of all the parameters that the physical neuron on our chip has. So what you can see here are then, example, some values. In this case, the leak potential and the leak eye bias. These control, as their name suggests, the leak voltage of the LIF model, and the leak eye bias is related to the leakage, the leakage conductance. And if you have set up this one neuron, then you specify that you want to record the membrane voltage, and then you can run it on the hardware. And this number is how long this experiment should be run. And Pine itself runs or uses natural units for neural networks. So in this case, this would be milliseconds. And in our case, this is actual wall clock time running on the hardware. So no conversion between biodomain and wall clock domain or something like this. So this just describes, okay, please evaluate what is running on hardware for 200 microseconds. And then we plot the result. So when we execute now this cell, I forgot to execute this cell. Then if you now execute it, you should see the slider, which you can, which just sets the value for the leak voltage. Then if you just slide it somewhere, you see, okay, the leak voltage is rising. And every time you adjust the slider, actually an experiment is run, sent here to Heidelberg, and is executed on the hardware. To note here, these values are in basically arbitrary hardware values of analog to digital converters and digital analog converters. So they don't have a explicit unit, but they correlate to, in this case, to a voltage. And also the readout is again in such arbitrary numbers, and it's roughly 0 to 1 volt is the translation roughly. And also what you should note is that the parameters given to the neuron, or to the neuron parameters, and the units for the readout don't correlate to each other. So don't be confused if you specify here 870 and it's only at roughly 600. Yes, so I think this should all be running for you. And of course, such a setup is not that exciting. And next we will look at a neuron that's firing, and this we do by configuring it in such a way that the leak is over threshold. Again, this is basically the same setup, but with some more parameters available. In this case, the threshold and the reset potential. And again, it's basically the same setup. So we can execute it. And then we see the membrane trace of this neuron that is continuously firing. So each of these events, or each of these points is the neuron emits a spike and is resetted to the reset potential. So again, if you just reduce the leak potential below, it's again a silent neuron. The leak threshold thing. So you mean in the new setup? So I hope everyone is somewhat familiar with the leaky integrate and fire neuron model. If not, I sadly don't have a backup slide. I mean, basically the leak potential is the potential where the neuron is converges to in equilibrium. And if the membrane voltage reaches the threshold, the neuron fires. So by design, if you put the leak over the threshold, the neuron will always decay back to the leak, and the neuron is fired. Okay. And you refer to this, so Mustang, you refer to a later point of the tutorial. Sorry, I'm a bit confused. So the problem is, so our neuron model is really just a representation, one-to-one representation, and some of these parameters are roughly translate to the actual live equation, but many of these parameters, which you will see here, are really just some parameters to get a neuron in a working state. And in this case, we only use the stripped down version of the edX model that only uses, so basically the edX model is a more complicated version of the live model, and we just ignore all these parameters, and for now we only use leak. And as a Synapse model, I think we currently only support conductance based, but I'm not sure. Do you
Only
know?
current based in Python.
Only current based for now. But in theory, we have both, but we don't support it for now. Or yes?
We already have calibrations in place for conductance-based synapses, but I'm not sure of the state in Pine so far.
Okay.
But
I mean,
you will introduce calibration later, so let's discuss this later.
Yeah.
And could you comment on the values? Because the graph looks like it is at the threshold looks like to be around 450.
Yeah. Okay. Yeah. That's another point. So again, these values are basically just arbitrary units that you control that are set somewhere, but they don't necessarily need to correlate to each other. In the case of the leak and the reset, they really correlate to each other, but the threshold is working on a different scale. So even if you set the leak, like 600 or so, so this absolute value is above the threshold value, but as they are not on the same scale, that's a problem, but this is typically handled by the calibration, which I will go into later on. So in a typical experiment, you don't need to worry about all these details, but it's just to give you an idea about the kinks of the hardware that you need to keep in mind to really understand it. So again, if you then put it to leak over threshold, and if you adjust the leak bias, you can see that this changes the time constants of the neuron. And also if you just slightly adjust it to rerun it, it's maybe not that clear. What you can see is, okay, the moment in time of the spikes is different in all runs. So this shows that this is not a real or not a software simulation where you just start always at a specific point in time and emulate or calculate the membrane potential. It is a real physical system running here all the time, and we only just look at a small snippet in time of this thing that is running continuously. Yes. I mean, that's a good point, Paolo. I mean, we try to give some insight about these parameters, but I mean, as you will see, I think I will just go to the calibration point of the tutorial. We can see that most of these parameters are taken care of in the future. So one issue is we have a lot of these parameters, and a typical user cannot understand all of them and should not. So there needs to be an automated way to handle this stuff. And one possible way to handle this is a calibration, which is also needed for the fixed pattern noise that is present on the hardware, because just of the nature of the CMOS process just leads to slight variations between the different neuron circuits. And to investigate these variations, we set up a population of 10 of our hardware neurons, and then just set them all to the same hardware parameters. So naively would expect that they all behave the same way. But when we actually look at them, so here we need to run, need to execute 10 different runs, because the readout, the readout of analog values, there are two ways to read out this stuff. One is a high frequency ADC, and one is a low frequency ADC. That the high frequency ADC can only read out one neuron at a time, but with a high accuracy. But we also have CADC, which has a rather low accuracy, but can read out many neurons in parallel. But for now in Pine, we only support the one high frequency readout. So therefore we need to run this 10 times so that we can investigate each neuron individually, which is set here via the population view. So, and if we then look at the result of this, we can see that some neurons just have different behavior. So all are set to the same hardware value, but the yellow one has a lower reset potential. The pinkish one has the highest threshold. And also they have different timescales because of this. So we need some way to alleviate this. And this is why we use a calibration, which automatically adjusts all these parameters to make the neurons behave more similarly. And and this calibration we use in we just provide you can run it on demand, but for this tutorial we just provide a static calibration that is run every night, which brings the neuron in a somewhat sensible state. So, and in the last part of this single neuron experiment, we will see what happens when we stimulate the neuron with external input. So first we load the calibration, and then what we set up here is again, so you can apply this calibration via Pine in the setup state. So in Pine setup, you specify which calibration you want to use. And this calibration then is automatically applied to all the neurons that you then create in such populations. And again, here we just want to look at one neuron. We record voltage and spikes, and then we provide some spike input. So we provide excitatory and inhibitory spike input in a way that we have some excitatory, some inhibitory spikes that we can see the dynamics of the neuron. So when we execute this, we see, okay, we have defined 6 input spikes overall, and 5 excitatory and 1 inhibitory. And you can adjust the different parameters. So the excitatory rate increases the effect of the input spikes, of the exciting spikes, and so on, the weight of the inhibitory spikes. And if you now want to get the neuron to fire, we can, for example, increase the excitatory rate, which is not enough in this case. But when we reduce the spike interval between the spikes that we send, we see, okay, now the neurons or the input spikes add up. And if we reduce it further, we can see that the neuron or the membrane potential reaches the threshold and really spikes. Yes, so yeah, this was the rudimentary introduction to how to set up a small network per se, but in this case only one single neuron. But I hope you got some understanding of how you can configure and set up such one neuron and investigate what is happening. And I will give you some minutes to try this out, and then I will also just switch to my colleague, which will then continue with the super spike learning rule example. So feel free to ask anything.
Björn has a hand raised.
And Björn. So
would it be easy to apply the calibration to this fixed pattern noise example? So is that a single statement that could be entered in there?
I mean, we have the calib thingy. We can just simply, the problem is, so what we can do is just simply call it here and don't override the values manually. So if we just comment this out, it will use the nightly calibration.
But it will not be lead over a threshold, right? Because the nightly calibration is just normal leadly integrated fire neurons.
Yes.
So the lead to 1,000, you should probably leave in there.
We still need lead over threshold, but then it should.
And final closing bracket.
Yes. Live coding.
What? No, not there. Down at the last commented out in the reset enable multiplication equals true.
It should.
Over there. Yeah, that's fine.
Yeah,
of course.
Yeah. Yes. So what you still will see is now they are much more closer to each other.
Much nicer.
What you still see is, of course, because these neurons are just configured with these parameters, but they continuously are running and they are not synchronized in any way. So some will just be shifted to each other. But
but that's not a neuron feature or
it's a
fixed pattern thing. It's just an effect of when this specific run was started.
Yes. And it's also just the nature of this analog hardware. It's just continuously running. It's not a simple simulation. Well, it's just not a simulation that is executed with all parameters defined, but every neuron is running for itself. And what we all also are currently working on is a version of this neuron that takes the parameters of this calibration, which supports a calibration run on each. It's not this, that is not using this magic calibration that is run nightly, but that is intrinsically supported in Pine, and where you can specify the parameters for the calibration, and the parameters for the calibration are not these completely abstract parameters, but are more related to the leaky inflated fire model. There you can specify like time constants and so on. And so that you in the future don't need to rely on this static nightly calibration, but can specify what you want, execute it once, the calibration is then run on demand, and then you can work with this calibrated state. yeah, but this is an outlook for the future. But
so right now
hopefully
you
soon
could, of
future.
course, also select an arbitrary operating point and
Yes.
run your own calibration for that. But that's, of course, much more involved than having it be handled automatically in Pine.
Yes.
And that's what we're working on.
Yes. So then if we don't have any further explicit question about this, I would head over to Johannes.
And you should probably stop your slide share.
Oh, maybe wait a
How
second.
can I
There's
set the
another
time
question.
constant?
Yeah,
Is another question.
Yeah, there's a question regarding the time constant. I mean, yeah, this is what we talked about. The problem is currently, I mean, in these parameters, there's no direct one parameter that corresponds to, for example, the time constant of the membrane potential, because it depends on the capacity of the membrane and the leak current. So basically you would need to adjust those two parameters to adjust the time constant. And this would be, or is one thing that you can specify as a target in the calibration, but in this tutorial, we don't present how you can run this calibration. We just take this one defined magic calibration that is run nightly. But you could, I mean, we have it. Yeah, we have it. You could run your own calibration where you specify your membrane time constant or other things. But sadly, we don't have the example handy right now.
So here in this example, if you leave the membrane capacitance constant, you could just adjust the leak I bias parameter to change the time constant.
Yes.
But of course, this value of 200 is arbitrary. If the unit is not something you can work with. And in order to say, I want this set to 10 microseconds, you would need the calibration. And this then generates an array of those parameters for all neurons that will result in 10 microseconds time constant for all neurons. Yes.
Okay, then I will stop sharing.